Hello and welcome to our bonus episode on feature selection. This is a follow-up to our series on neural networks where we built a neural network to identify JIRA tickets that were likely to cause trouble in our production pipeline. We ended up with a functional AI tool, but we couldn't explain why tickets were being flagged. In this series, we'll be using feature selection to pare our inputs down to just the most important ones. We'll let managers know what they are so they can start being proactive in building programs to address those factors and smooth out their software development process. This is not the standard use of feature selection. Normally, it's done at the front of your data science project while you're exploring a data set. We're using it instead to hack a finished neural network, to reverse engineer it and learn more about how the inputs drive the output. Chiefly, this presentation allowed us to more quickly get through all the steps in building a simple neural network. And now we can see a new use for feature selection. Before we begin, let me review our setup. So I'm using Python 3 inside a Jupyter notebook, which I got by installing the Anaconda package. And my example company here uses Jira Server and installed the IonaFX Business Intelligence Export add-in. That gave us a report and a web server, some other things. We ran the report and we got a CSV file containing Jira issues that were added or updated over a given period of time. We then piped that data into a neural network that we created in a previous series. I'll put a link to it in the description. It predicts, based on our historical issues, which of our current issues will become problems. And we'll use that code as our starting point. Let's also just talk about feature selection for a minute. So feature selection's goal is to reduce the dimensionality of our inputs. And that's to reduce the number of columns, the number of features that we're feeding into our model by identifying and selecting only the highest quality and most informative features. So how is it that you go about selecting certain features that are important? Well, there are some different ways to do it. And let's start with the univariate techniques. Here, we would look at each feature and find its relationship to the variable that we want to predict. We can use things to measure the strength of that, like a chi-squared or an ANOVA-F value, and then we'd rank the variables by these scores and keep only the ones with the highest scores. When we rely on single variable relationships, though, we aren't checking for relationships between those variables. And this could lead us to build duplicate or otherwise unnecessary information into our model. Instead of building features from the bottom up like that, we'll use a method that works from the top down, starting with all the variables that we have, and then recursively eliminating input variables and testing the impact on the model's performance. And then it uses cross-validation to check that we haven't by chance picked a set of test rows that work well with some combinations of variables, but maybe not with others. And it also helps us find the point where eliminating more inputs would lead to worse predictions. It's called RFECV. To begin building it, let's create a new notebook and start coding. Now, as I mentioned, this is a follow-up from our neural network series. So what I'm going to do is make a copy of this and just rename it to, there we go, to something new called feature selection. And right up here at the top, we are going to need to add two more libraries. First, we want the feature selection process itself. And that is from scikit-learn.featureSelection. We will import RFECV. That stands for Recursive Function Elimination and Cross-Validation. And that's what we talked about above a little bit. And second, we'll import an estimator that can be used with this RFECV process. I'll talk about that in a second here. scikit-learn.svm, that's support vector machines. And we're going to import SVC, which is a support vector classifier. And as is sort of suggested here, it's a support vector machine applied to a classification task. It builds a representation of the observations as dots in space, kind of like a scatter plot. And it's arranged so that examples of the separate categories, like red flagged issues or not red flagged issues, can be divided up by a ribbon of empty space that is as wide as possible. And then any new observations that we collect, we can post into that same chart, and it'll be predicted to belong to a category based on which side of that ribbon's center line they fall. With our libraries imported, we can put them to use. I'll scroll down to my Create, Test, Train, and Prediction Datasets section. And in here, I'll create a new section where I can run the RFECV analysis to pull out some more informative features. I'm going to create it right after I've defined XT and XY. Edit split cell, and I'm going to create a cell above it just so I can give it a name. We will call it feature selection. Then I'll create a space for me to enter some code. And in this new section, the first thing that I'm going to create is an estimator object. That's one of the SVCs that we imported, and that's necessary. It provides a metric which my RFECV process can use to judge the feature's value each time it loops through my data. I'll call it SVC, and it is an SVC object, and the kernel I will use is linear. So this linear kernel is going to try to find the one straight line that best separates red flagged issues from not red flagged issues. And we're using a linear kernel because it has a coefficient attribute. And that's the actual metric that the RFECV needs to determine which attributes are more important than others. Next up, I'll create the RFECV process itself, and I'll just call it RFECV equals an RFECV. And here I get to pass it a few parameters. The first one will be the estimator that we created up there. And it's called estimator equals SVC. Next, I'll add the step parameter, and that tells the algorithm how many features should be removed in each pass. And I will just remove one feature in each pass. And next up is my cross-validation generator. It's called CV, that's the parameter's name. And this determines the number of folds that my data set will use, where one of those folds would be the test set, and the rest are the training set. And I'm going to use, I think, 5 folds here. It's really common to use 10, but we just don't have enough cases where red flag is true. So if I use more folds than that, I'm unlikely to have enough positive observations in all of my test folds. If you do have enough positive observations, though, go ahead and use a few more folds, and you might even try stratified k-fold, which would attempt to balance out the number of positive and negative outcomes in each test set. And the last thing that I want to add here is scoring. And this is actually a very cool parameter. You can pass in your own scoring function. I'm just going to use a simple one here, accuracy. Because we don't have a complex data set, we don't need anything too fancy. And accuracy will give us a score that's proportional to the number of correct classifications that were made. With that all done, I can go ahead and fit my data into this. So rfecv.fit. This is very similar to how we fit the data for our neural network model. In fact, I'll pass in xt and I will pass in yt. And again, this fit method expects to have an array of values, and yt is a data frame. So what I want to do is go, it's a one-column data frame, so I'll get values out of that, and I'll use the ravel function to unpack them into an array. Now with this built, we've got a chance to give the manager some useful information here. We can take a look at the original number of features that we had, the number of features that were determined to be important, and we can even get their names. So let's do all of that right now. First, I will print out the original number of features. Use %d. And then length of xt.columns. And next, I'll print out the number that we reduced it to. And that is, and I'll just call it number of important features. And to get this, we can, RFECV will provide us with a very useful attribute called nFeatures, with an underscore at the end of it there. That displays the number of output features. And that's all very neat, but now we want to know the names of those features, and there's another attribute very useful like nFeatures here called getSupport. And we can use that to get a Boolean mask of which features were important or not, which we can then use against our xt columns here to get their names. So let's set that up. I'll call it ivars selected equals xt.columns.values rfecv.getSupport. And we want to change that over to a list. Now we'll have, like we have ivars and dvars, now we'll have the ones that were selected by our RFECV function. And while we're here, we may as well rebuild xt, because now we only want to have those important features in it. So I'm going to say xt equals df done, and just pass in ivars selected. And then let's print it out while we're here. And then if we've done all this to our training set, we should also do it to our prediction set, which was down below here. So df not done, instead of being ivars, we can change that to ivars selected. Well, let's run this and see how it works. And I can see one mistake that I made. I'm not sure why I did that. Just typo. All right, it appears that we have reduced our original number of features, 37 columns, down to just 1%, estimated time. Now this percent estimated time is a calculated column. We added that to our data set. It was based on the original estimate and the total time spent. So we could technically not have done this bit, and we'd probably get out those two features instead. However, what is important here is now we have some things that we can tell to managers. We need to pay attention to what forms percent estimated time, which is the original estimate. Maybe they can work on their team's estimation skills a bit, or maybe they can divide some projects, some issues into a series of smaller subtasks that are easier to manage. It could be estimated a bit better. And then total time spent, which is the just amount of time logged on an issue. They can certainly work on both of those things with maybe chopping tickets up into smaller subtasks. Let's go on down and see how our model performed with this, because we're just passing in one thing now. Interesting here. So we get the same precision, and if you recall, this precision number is the proportion of positive identifications that was actually correct. And we're still at 1 here for both our red flags and our not red flags. That means that when our model predicts an issue to be a red flag issue, like here it's predicted it to be a 1, it is correct 100% of the time. And when it predicts that it's not a red flag issue, it's also right 100% of the time. And then we have recall over here. That's the proportion of all actual positives that was identified correctly. That's sort of, did we miss anything? So our model correctly identifies 100% of all the red flagged issues that were in the test set, and not red flagged issues as well. And let's scroll on down to where we have our predictions, and they match up with the predictions that we got before, but now we're only using one variable to make those predictions. That is feature selection at work there. It provided us with two really important benefits now. Our neural network has a lot less work to do, and we now know the names of the most important features. We can tell everyone, hey, pay attention to the things that make up percent estimated time, being original estimate and total time spent. In fact, we might even want to build those things into a dashboard so managers and developers can see it every day. And I should probably mention that I can help you with that too. I have videos on building dashboards in Power BI and even Excel. I'll put links to those down in the descriptions. I hope you had fun with this bonus episode on improving your neural network with feature selection. Thanks for watching. Bye.